notice. Yes, yeah. We have finished the whole 9 chapters. We will continue your PBL report and the team project presentation today. Yeah, we will start the PBL report of Simen and the additional explanation on some important problems in chapter 9. We will start with Simen. Okay, here.
Good afternoon, everyone. I'm Simen, team leader from Team 6. I had marked a couple of the problems that I wanted to go through from chapter 9 again. Since I only have 10 minutes for the PBL report and the projects and the solutions, I think I only have time to go through a couple. Where is the solution? Yeah, okay, the solutions that I was referring to. Okay, I think I have them in the bottom anyway. Yeah, so our team leaders are me, Piran, Angel, and Jennifer. And our team project topic was Dijkstra's algorithm. And the optional second team project was binary trees. Yeah, starting as previously, stating definitions and concepts that we learned and explaining them relatively shortly. Trying to cover the most important concepts from the various 9 chapters. Also stating things that you know or can find from the chapters divided in chapter 1 to 5 and chapter 6 to 9. Also trying to catch the essence, I guess, of the course. Yeah, the reflection notes, I feel like I contributed pretty good in the Q&A. But I think I also could have made more discussions or added more to discussions or asked questions to inspire discussions instead of simply solving exercises and reviewing and finalizing other students' exercises. Yeah. And I think the learning activities in this course is quite unique, which you have to put in an effort by coming prepared to class, by contributing in the Q&A and so forth. But I think if you do those things, you'll enjoy the curriculum much more than if it was lectured in a regular fashion. As I think one of the most important things for studies is to prepare before class. And this course kind of forces you to do that. Yes. Yeah. Yeah, I also think in addition to improving my mathematical and discrete mathematical skills, I think this course has also contributed to improving both my communication skills and my presentation skills. As again, you're forced to kind of step out of your comfort zone and present the PBL report and so forth. Yeah, yeah. Yeah, that's true. In fact, it's not negative. It's neutral. I guess it's more just the fact that didn't see that much practical applications of it, I guess. Yeah, and also by communicating in a language other than my mother tongue and presenting, I think it's a very good experience that I will benefit from in the future. Yes, I don't think I have that much time, so I think I'll skip down to the project. Sorry? 86, I think, yeah. So yeah, our project, Dijkstra's algorithm, where my role was team leader, I guess also solving, typing, and presenting. And as you probably all know by now, since we've gone through chapter 9, is that Dijkstra's algorithm is a dynamic programming algorithm to find the minimum path. That means the path with the minimum cost from a given source node and to all the other nodes in a graph. And this has a lot of practical applications. For instance, you can model routers and switches in a computer network, and the edges as the connections between them, or you could model it as cities, and the edges would be the roads between them and the cost, or yeah, so you can model postal services or whatever. So it has a lot of practical applications. And the worst case time complexity of the algorithm is big O of E plus V log V, where E is the number of edges and V is the number of vertices in the graph. You should note that this is when the algorithm is implemented by using a minimum priority queue. And I think the original algorithm by the mathematician, the Dutch mathematician Dijkstra, wasn't. So then the worst case time complexity, I believe, was V to the power of 2. Yeah. Oh yeah. This was the draft. So the full thing is for.
The Dijkstra algorithm is a good algorithm, but that's not the best one. There are other the better performing algorithms, but that's the important standard algorithm that you're supposed to know.
Yeah, and I guess you kind of have to learn that before moving on to the more complex ones. I'm just going to go to the full PBL report. No, not the full project. Yeah, like I said, the original algorithm was not modeled with the mean priority queue, so it's become worst case big time complexity, big O notation was V to the power of second. And I would like to visually explain how the algorithm works by using these pictures gathered from this website, where we choose C as the starting node. And we start by initializing the distance to all the other nodes as infinity, as you can see here in blue. And Dijkstra's algorithm will then consider all the costs. So from C to B, we see that it's not infinity. In fact, you can go and get there in 7. So this will be updated to 7, and accordingly with A and also with D. And then the algorithm simply chooses the one with the least costs, which is A. We visit A, and then both of these are added to the set, and then we simply repeat the process from A. So A only has one other node directly connected in addition to C, which is B. And we can see that we can get from A to B with a cost of 3, but we need to remember that since this is Dijkstra's algorithm, so we try to find the minimum cost from the source node, not just from the subgraph. So in addition to 3, we have to add it with 1, obviously, because we want this entire path. And we then update the minimum cost to get to B to 4, because we see as this path is more efficient than this path. And this is kind of the essence of the algorithm, that it updates the minimum cost of getting to the various nodes. So it's not a greedy algorithm, like, for instance, Prim's algorithm. Yeah, so Yeah, we update the costs of getting here, but we also see that the cost of getting from C to D is just 2, whereas the cost to get to B is obviously 4. So therefore, D would be the next choice to add to the set. So we will visit D. And again, continue the process, update the cost to E, as we can get here in 2 plus 7 equal to 9 instead of infinity. And we also can reconsider visiting B. We see here that this would equal a cost of 2 plus 5, 7, but we already have 4, so we abandon that. And yeah, then we visit B, obviously, because the cost here is less than the 9 here. And then lastly visit E, and then all nodes have been added to the set, and we have found the minimum path from C to all the other nodes in the graph. Obviously, a real-life graph would be much more complicated and with a lot more nodes than this. But then again, it would be happening a lot faster. Yeah, and this is the pseudocode for implementing the Daxus algorithm, which Piran was supposed to present, but he's not here. But it's mainly that you keep adding these to the set and update the cost and always compare it with the previous costs. There's always also a Python script here to find the Daxus algorithm. And then on to the second team project about binary trees. Where I guess I mainly tried to outline the various types of binary trees and also their practical applications. Obviously, binary trees are just 3 data structures, which has a maximum of 2 nodes, referred to as the right and left child. And you can kind of divide them into 2 main categories as a way to access node. Yeah. Okay, yeah, we can use it for a lot of practical implications, like, for instance, Huffman code, like I explained last Wednesday, and also implementing binary search trees for very efficient sorting and searching of data. And as you probably also already know about like the complete trees and the perfect binary trees as to how much nodes the various, or how many children the various nodes have. Also, if I have time, let's talk very briefly about the binary search trees, which makes for a very efficient search, where every right child will be bigger than the parent node and every left child will be smaller. And this makes for a very efficient search as long as the binary search tree is balanced. Because the worst case will be something like this, which still fulfills it's still a binary search tree, as the right child obviously is bigger than the parent, but it's not balanced at all because there's no nodes on the left side, but everything is on the right side. So the time complexity of searching for an element here would be just big O of n, because this would basically just be like searching linearly through a array. Yeah, these are my final PBL comments from the various months. And I think, yeah, the last few chapters flew by very quickly, probably due to a lot of new teaching approaches, using a lot of flipped learning, even more teamwork by dividing us into the teams and making each team prepare questions for different chapters. And this also greatly boosted my Q&A activity. Yeah, and finally, I think the course has been a lot of work and taxing both in terms of subject and in terms of communication. But nevertheless, I feel like the course has got me out of my comfort zone and therefore given me more than just the increased knowledge within the field of discrete mathematics.
Explain all three problems, good problems.
Okay.
Would you like to share?
Yeah, so let's see, we start.
Good explanation.
I'll try. You could do that one. Do the one about Prim's algorithm, or not that one, but yeah, the next one. So Prim's algorithm, at first glance, may be a bit similar to Dijkstra's, but the important difference is one, you don't reconsider the cost of visiting previously visited nodes, and also you consider the cost from the subgraph, not a given source node, like you do in Dijkstra's. So if you can use Prim's algorithm to create the minimum spanning tree of this graph, starting from the initial vertex 1, then it would start sort of similarly as Dijkstra's. We will consider these costs, weights of these edges, and we see that 2 is the least, so we visit node 4. We see here, draw this line, and then instead of considering the path to, for instance, 7 as going through 4 and adding these costs together, we simply look at this cost, because the subgraph now consists of both these nodes, and all the other weights we consider are weights for edges that are connected to the subgraph. So then the next one would be to connect to node number 2. As 8 is the least of these costs, you can see 8, 24, 18, and 16. And we continue in this fashion until all the nodes are connected and we have connected, or we have made a minimum spanning tree. I think maybe I can also, if I have time, explain the Huffman coding again. So Huffman coding is a sort of compression algorithm to compress text. So given these letters and their frequency in some string, we create this tree, and we do that by modeling all the letters as terminal vertices, and with their corresponding frequency, and we simply add together the nodes with the least frequency. So you see the least of all of this will be 5 and 5, which together results in 10. And then we have 10, we have 8 and 10, so we can choose if we want to. So obviously there's several optimal solutions here, but we go for this one where we add 2 and 8 to 18. The next one would be adding 10 and 12 to 22. We continue in this fashion until we come to the root node. Then we model every left edge as a 1 and every right edge as a 0. And then we can simply find the code for every letter by simply tracing the path from the root node and down to the given letter. And I don't. Yeah. Yeah. This is more actually about what we actually do, but I think what fascinates me the most with Huffman code is that how simple it is, and the result of the resulting code isn't just that it takes up less amount of bits and takes up less space, but you can also put them directly after each other, and you don't know, obviously, since these are variable length, they have different lengths, but you can put them like, for instance, if we write 1 1 0 1 1 1 0, then even though you don't know how, like when one value starts and when the next begins, you can still, there's only one way to read it. So you simply can see that this can only be this one, because there's no other. If you only consider these two, there's no letter just symbolized by 2 1s. So there's only one way to read it, as simply 1 1 0. So this must be a B, and then the next one must start here, and from here on this must be a C, so forth. And this works however long you make the binary string. Yeah, I think that's all I have time for. So thank you.
Question or comment from Simon's?
Any questions or comment?